These are our notes for implicit differentiation. So before we talk about how to differentiate implicit equations, we need to actually define them and talk about what they are. So we're going to talk about explicit equations versus implicit equations. If you can solve for one variable, and to start, let's just call that variable y. If you can solve for y in terms of another variable, say x, using only one equation, then what we say is that y is expressed explicitly in terms of x, also known as y equals f of x. This tells you that y is explicitly defined as a function of x. These are in fact functions. So for example, if you have y equals x to the fifth sine x under a square root, it's explicitly solved for y. That's an explicit equation. It's a function. Or y equals the quantity x minus 4 divided by x squared plus 1 all cubed. That's an explicit equation. If instead x is expressed explicitly in terms of y, also known as x equals f of y, then you have x as a function of y. For example, if you have x equals y squared plus y minus 3, that is x as a function of y. If x equals cosine y, that's also x as a function of y. So you don't want to get too locked into, hey, we're solving for y in terms of x. We can use any types of variables going on in here. Let's compare that to implicit equations. So implicit equations can't or can't easily be solved for one variable, either at all, meaning it can't be solved for one variable at all, or it can't be solved for one variable without the use of multiple equations. So for example, if you have y to the fourth plus xy equals x cubed minus x plus 2, solving this, frankly, for either x or y, if it can be done, is going to be exceptionally difficult to make that happen. For example, also x squared plus y squared equals 9. I wouldn't say it's difficult to solve this for x or y, but watch what happens if you try. Let's say for the moment I decide to solve this for y. This should look pretty familiar. Because you see x squared and y squared and the coefficients in front of them are the same, this is a circle. Specifically, this is a circle centered at the origin that has a radius of 3. And you may recall from pre-calculus, if you want to put this into your graphing calculator, there's a little bit of a cheat. You can solve it for y by saying, hey, y squared equals 9 minus x squared. So that y is going to be equal to, now you square root both sides, but you have to make sure to put a plus or a minus in front of the square root. And if you put the positive square root of 9 minus x squared in your graphing calculator, it gives you the upper half of your circle, centered at the origin, radius 3. And then when you put the negative root in, it'll basically give you the lower half of the circle. And that's kind of a cheat on how to get a circle into a graphing calculator. So you can solve this for y, but notice how many equations it takes to make that happen. It takes 2. So this is an implicit equation. So what we want to do is we want to talk about how do we take the derivative of equations if you can't solve for x, or you can't solve for y, or you can't solve for a single variable, at least not easily. So we want to talk about finding DYDX. And when we're looking for DYDX, that pretty much explains to us the role of each variable within our equation. It tells us that x acts as a variable, but y is a function of x, or y equals y of x. The derivative of any expression containing y requires chain rule. Okay, y is an entire function. So when you see something like y or y cubed just kind of sitting around somewhere in an equation, its looks can be a little deceiving when you go to take its derivative. It looks like, oh, I just use power rule. Drop down a 3, take y to the new power of 2. But what you have to remember is that this is some unknown function of x cubed. So when you go to take its derivative, that's a chain rule. So for example, using implicit differentiation, find dy dx for x squared plus y squared equals 25. So again, that's a circle centered at the origin with a radius of 5. Okay, and we're going to try and take the derivative of this. So step one, we're going to take the derivative. This is with respect to x. We can tell that because of the dx in the denominator. And we're going to take the derivative of both sides of the equation. Okay, it's a similar principle that we've been using in algebra for a long time. As long as what you do to one side of the equation you also do to the other, it's legal. So if we take the derivative of x squared plus y squared equals 25, the derivative of x squared, because x is a variable, is just 2x. The derivative of y squared, however, remember, that's an entire function squared. We just don't know what that function is at the moment. So we drop down the 2. We don't touch the inside function. Well, the inside function, we don't know exactly what it is, but it's y is what we're calling it. Raise it to the new power, which is 1, times the derivative of the inside function. Well, since the inside function is y, its derivative with respect to x is DYDX. So that's the derivative of y squared, and then equals. We then take the derivative of 25, and since that's a constant, its derivative is 0. Next, what we're going to do is find DYDX. We're going to solve for that DYDX. So we take DYDX, we subtract the 2x over to the other side, and we divide by 2y, which is currently being multiplied times the DYDX. So when you simplify, DYDX is negative x over y. Okay. A couple of things to keep in mind with this. When you're using implicit differentiation, it is not unusual to have both x's and y's in your derivative. And believe it or not, we have been, in essence, taking these steps even for equations that are explicitly defined in terms of x. I mean, if I give you something as simple as y equals, 3x to the 5th plus 2x, okay, we've been taking this derivative for a few sections now. You are taking the derivative of both sides of the equation. It's just that the derivative of y with respect to x is DYDX. So you're already solved for DYDX on the left side. And then when you take the derivative on the right, you're going to get 15x to the 4th plus 2. So these steps for implicit differentiation aren't really new. We're just having to be a little more particular about how we're discussing them because we weren't able to solve for y as a function of x. So let's take a look at this example. Use DYDX to find the slope of the tangent line to the circle x squared plus y squared equals 25 at 3, 4. So from the previous slide, this is the same equation that we just took the derivative of. We found that DYDX was negative x over y. That's what we just found on the previous slide. So in order to find that slope, we need to find DYDX specifically evaluated at 3, 4. Plugging in 3 in place of x and plugging in 4 in place of y. So that's negative 3 over 4. So just like explicitly defined equations, DYDX still tells us the slope of all tangent lines. If you want the slope of a specific tangent line, you plug in the point you're using. The only difference is now we need to plug in both the x and the y. So once we have a handle on that, let's take a look at this for a moment. Pretend for a moment that we hadn't completed the example on the previous slide, that this DYDX was unknown to us. How could we answer this question without implicit differentiation? So we've got x squared plus y squared equals 25. We're still looking for slope of a tangent line. If you remember, we were able to, because this was a circle, solve this for y. Now, the penalty, because this is an implicit equation, was that we had to use a plus or minus in front of the square root, which means we needed 2 equations to make this happen. So this one is actually y equals plus or minus the square root of 25 minus x squared. Now, if the question just said find the derivative, find DYDX, we wouldn't really be able to do that too easily because we wouldn't know, should I use the positive square root or should I use the negative square root? But that's not what this question is asking. This question is saying use DYDX to find the slope of the tangent line at 3, 4. Well, remember what I said about these circles when you go to graph them? The positive square root gets you the upper half of the circle. The negative square root gets you the lower half of the circle. Well, if I'm looking for the slope of the tangent line at 3, 4, which of the two functions should I use? The positive square root or the negative square root? Well, because we're looking at a specific point, we know to use the positive square root. So we're going to use y equals the square root of 25 minus x squared. So once we know that, we can find dy dx by taking the derivative technically of both sides. The derivative of y with respect to x is just dy dx, and then we use a little chain rule. 1/2, don't touch your inside function, 25 minus x squared, to the new power of negative 1/2 times the derivative of the inside function, which is negative 2x. Clean it up just a little bit. The 2 in the denominator of the 1/2 will cancel the 2 in the numerator. We're just going to be left with a negative x in that numerator. And then the 25 minus x squared is currently to a negative exponent, so to make that positive, we'll put it down in the denominator. But instead of writing it as a 1/2, I'll put it in as a square root. So that's negative x over the square root of 25 minus x squared. That's my dy dx. Now notice if I wanted to finish this, all I need to do, instead of plugging in both x and y, I would just need to plug in x. So dy dx evaluated at x equals 3 is going to get me negative 3 over the square root of 25 minus 3 squared, which is 9. That's 16. So that's negative 3 over 4. And notice that's exactly the same as the answer we got above. So in this particular instance, because we were able to solve for y and then choose which of the two equations we could use, we actually could get around implicit differentiation. If you can't solve this for y, you're going to need to use implicit differentiation. But that's actually not why I did this. I want you to take a look at something really quick. Look at that dy dx again before we plugged in an x value. Notice it's negative x over the square root of 25 minus x squared. What was it we got as the derivative on that previous slide? We got negative x over y. Here we got negative x over 25 minus x squared. But remember what y was? How did we get that? Y was the square root of 25 minus x squared. So when you're using implicit differentiation, whether or not you know what y's explicit definition is, you're still able to take its derivative. Hopefully that illustrates the general idea of implicit differentiation. Let's take a look at some examples. Let's find dy dx for y equals 4x to the 5th plus 2y to the 9th. Even though we have a y isolated on the left side, this is not solved for y because of the fact that you still have a y to the 9th on the right side. So we're going to take the derivative of both sides of the equation. The derivative of y with respect to x is dy dx. The derivative of 4x to the 5th with respect to x is 20x to the 4th. And the derivative of 2y to the 9th with respect to x, remember y is an entire function, you're going to get 18 when you bring the 9 down to multiply times the 2. The inside function is called y. It now has a new power of 8. But now we need to multiply times the derivative of that inside function, so times dy dx. Once we have that, we need to solve for dy dx. And this one's going to be a little bit challenging than the last one we did, because of the fact that dy dx doesn't show up once, it shows up twice. So the technique when you need to solve for anything that shows up twice in your equation is to move every term that has what you're looking to solve for, in this case that's dy dx, to one side. So I'm going to move this 18y to the 8th dy dx to the left side of the equation. So I'll have dy dx minus 18y to the 8th dy dx. And then any term that doesn't have a dy dx is going to stay on the right-hand side. What that's going to allow me to do is notice the two terms on the left now have dy dx in common, which means I can factor it out. So I get dy dx times 1 minus 18y to the 8th equals 20x raised to the 4th power. Now I'm down to 1 dy dx in my equation instead of 2, so I can solve for it. The operation going on here is multiplication, so I'm going to divide so that dy dx equals 20x to the 4th divided by 1 minus 18y to the 8th. And that's my derivative. Let's look at another example. Find dy dx, so we're still looking for the derivative of y with respect to x, for y to the 4th plus xy equals x cubed minus x squared y. So we take the derivative with respect to x of the left side. Y then is a function, so its derivative is 4y cubed, but that's got an inside function. This is chain rule, times dy dx, plus, now be careful on this xy. That is a product. That's multiplication between them, so you have to use product rule to take that derivative. The derivative of x with respect to x is 1 times y plus x times the derivative of y with respect to x, which is dy dx. Then we take the derivative of the right side. The derivative of x cubed with respect to x is just 3x squared minus x squared times y. That's again a product, so we have to use product rule to take its derivative, and the subtraction sign in front applies to all the terms that come after. So I'm going to open up a set of parentheses. So the derivative of x squared with respect to x is 2x times y plus x squared times the derivative of y with respect to x. Okay. This time we actually have 3 dy dx's to solve for. So any term that has a dy dx, I'm going to move it to the left side. Over there we already have 4y cubed dy dx plus x dy dx. And then on the right side right now, technically because of the negative out front, this is minus x squared dy dx. So to move it to the left, I'm going to add it. So plus x squared dy dx. Okay. On the right side, we already have a 3x squared minus 2xy. And then I need to also subtract over the y to the right-hand side. Okay, factor out the dy dx. We are left with 4y cubed plus x squared equals 3x squared minus 2xy minus y. And then since we're down to 1 dy dx, we can just solve for that by dividing this over to the other side. So dy dx is 3x squared minus 2xy minus y over 4y cubed plus x squared. And that's the derivative for this one. Let's change up some of the variables just a little bit so we can start to get a look at what that's going to look like. Find dy dt for cosine of ty equals t squared divided by y. Okay, so t acts as your variable, y acts as a function of t. So y equals y of t. That's what my notation is telling me. So when I take the derivative of the left side, the cosine of t times y. So we take the derivative of the outside portion first. The derivative of cosine is negative sine. And then we don't touch the inside function. Leave the t times the y. But now we need to take the derivative of t times y. And y is a variable and t is a function. That means that's a product rule. So I'm going to open up a big set of parentheses here. The derivative of t with respect to t, since that's your variable, its derivative is 1, times y plus t times the derivative of y. But y is an entire function, so its derivative is dy dt. Okay, that's the derivative of the left side, equals. So we have t squared divided by y. You can either use quotient rule or you can treat this as t squared y to the negative 1. Either one's great. I'm going to go ahead and use quotient rule, but using t squared y to the negative 1 would be just as correct. So I will have the denominator times the derivative of the numerator, and since t squared is the variable, its derivative is just 2t, minus t squared times the derivative of y, which is my function, so its derivative is dy dt, all over the denominator squared. Okay, so again, we need to solve for dy dt. Okay, so there are two of them, one on the left and one on the right. So let's see, I can move the y squared, multiply it over to the left side so that I have negative y squared sine of t times y. I'm going to go ahead and leave this at the moment. Inside the parentheses on the left, this simplifies to y plus t times dy dt. That's a plus. And then that will equal 2yt minus t squared dy dt. So on the left side, we're going to need to distribute the negative y squared times the sine of ty to both terms, so that we get negative y cubed sine of t times y minus ty squared dy dt. That's just distribution. And then the right side, I'm not going to do anything to it yet. Keep it the same. So then we want to move every term with the dy dt to one side and every term without to the other side. So again, I'll just take everything with the dy dt and move it to the left. It doesn't really matter. So you get negative ty dy dt. That will be plus t squared dy dt equals 2yt on the right, and then move over the y cubed sine of ty. So plus y cubed sine of ty. Factor it out so that we get dy dt, and then divide it to the other side. So I'll leave the 2yt plus y cubed sine of ty divided by, and that will be, I'll just reverse the order so the positive one goes first, t squared minus ty. That should say sine, in case that's not clear. So that's the derivative for this one. So changing this to dy dt instead of DYDX doesn't change much, except that y is now a function of t. So anytime you take a derivative involving a y, your chain rule contains a dy dt instead of a DYDX. This example has a change that's a little bit more profound. We've gone back to x's and y's, but notice in this question I'm not asking you for dy dx. Instead, we're asking you for dx dy. That is the derivative of x with respect to y. So that tells you that y acts as your variable, and x is now considered to be a function of y. So x is an entire function. That is the letter on which you will now have to perform chain rule. You are now going to have to use chain rule for this, for x. You don't actually know what that function is, but you do know it's a function of y. So when you go to take its derivative, the chain rule, the derivative of your inside function, will be the derivative of x with respect to y. So let's take a look. If we want to find dx dy for x to the fourth y squared minus x cubed y equals 2x times y cubed. So each one of these individually is a product rule. So let's take a look at x to the fourth y squared first. So x to the fourth is an unknown function to the fourth power. So its derivative is going to be a chain rule. It's going to be 4 times that unknown function to the new power of 3 times the derivative of the inside function, which, since we don't know what the inside function is, we just call it dx dy. So that's the derivative of x to the fourth times y squared plus x to the fourth times the derivative of y squared with respect to y. Well, that's just 2y. So that's our first product rule. Let's take a look at the next one. Notice there's a subtraction sign in front of it, so I'm going to open up a set of parentheses. The derivative of x cubed with respect to y is going to be 3x squared dx dy times y plus x cubed times the derivative of y with respect to y, which is just 1. Okay. Then finally, we'll have a product rule on that right-hand side as well. Usually, if there's a constant, I'll go ahead and pair up the 2 and the x together as my first function and leave y cubed as my second function. You could alternatively just leave the 2 out and perform the product rule only on x times y cubed. That would be correct as well. But I'm actually going to treat 2x as my first function. So the derivative of 2x with respect to y is 2 dx dy times y cubed plus 2x times the derivative of y with respect to y, which is 3 times y squared. So once we have all of that figured out, we can go ahead and just go about our business as usual. We need to solve this for dx dy. There are 3 of them in this equation. So every term that has a dx dy stays on, I'll keep it on the left, and every term that doesn't have a dx dy, I'll move it to the right. So my first term, I'm just going to reorder it a little bit. So that's 4x cubed y squared dx dy. I just moved the y squared up front a little bit. Currently on the left side, I already have a minus 3x squared y dx dy. I moved this y up front. And then over to the left side, I'll be moving from the right minus 2y cubed dx dy. Okay. Currently on my right side, I also have the 2 times the 3 will give me 6xy squared. And then I'm going to move over the x to the fourth times 2y, so minus 2x to the fourth y. And then on the left side, it's currently a minus x cubed, so when I move it to the right, it'll be plus x cubed. Factor out my dx dy, so that dx dy times 4x cubed y squared minus 3x squared y minus 2y cubed equals 6xy squared minus 2x to the fourth y plus plus x cubed, and then just divide it out. So dx dy is going to be equal to 6xy squared minus 2x to the fourth y plus x cubed, all divided by 4x cubed y squared minus 3x squared y minus 2y cubed. That is my derivative of x with respect to y. Okay, let's look at one more example. We're going to find the points at which the graph of 25x squared plus 16y squared plus 200x minus 160y plus 400 equals 0 has a horizontal tangent line. So we're back to talking about horizontal tangent lines. And what we know is that if a tangent line is horizontal, its slope must be equal to 0. And since the slope of the tangent line is also known as DYDX, these kinds of questions say find the derivative and find out when it's going to be equal to 0. Okay? This one is an implicitly defined equation. So when we take the derivative of the left-hand side, the derivative of 25x squared, these are DYDX's. So the derivative of 25x squared with respect to x is going to be 50x. The derivative of 16y squared is going to be 32y dy dx. The derivative of 200x is just going to be 200. And the derivative of negative 160y is going to be negative 160 dy dx. The derivative of 400, since it's a constant, is 0. And then, of course, the derivative of 0 is also 0. Okay? We still are going to solve for DYDX. So on the left side, if we factor it out, I would have 32y minus 160. And then on the right side, I'll move over the negative 50x minus 200. So that DYDX is equal to negative 50x minus 200 divided by 32y minus 160. There are some other algebraic simplifications you could do. For example, you could factor a 2 out of both the numerator and the denominator and cancel them, but I'm not going to do that at the moment because what I'm actually looking to do is to set this equal to 0. So what I need to do is take this fraction and set it equal to 0, but a fraction is only equal to 0 when its numerator is equal to 0. Okay, so if we solve this for x, we would add the 200 and divide by 50. So x equals negative 4. Once we have an x value, what we're looking for are points. So that means we're not going to plug our x into our derivative, because if you input an x into a derivative, you get the slope of a tangent line. What we're looking for are y values. So we're going to plug x into the original function. So we're going to take 25 times negative 4 squared plus 16y squared plus 200 times negative 4 minus 160y plus 400 equals 0. So 25 times 16 is actually 400. So we have 400 minus 800 plus another 400. So the constants on this side actually all cancel out. So we get 16y squared minus 160y equals 0. If we factor out the 16y, we then get y minus 10 equals 0. So that tells me that y equals 0 and y equals 10. So my two ordered pairs are going to be negative 4, 0 and negative 4, 10. Those are the 2 points on this graph that should have a horizontal tangent line. So that's implicit differentiation. We haven't really shown you what it is we plan on doing with it other than just taking derivatives, but its applications are numerous and they will be coming up very shortly.